Very good morning, students. Today we discuss about the module called as lubrication and bearings. As discussed earlier about the introduction part of the lubrication and bearings, now today in this class I am starting with the Petrof's equation. So in this Petrof's equation I am considering a full journal bearing. The word full journal bearing indicates that the journal is completely covered with the bearing. So we call it as a full journal bearing. If a journal is if the journal is covered with the bearing of particular angle, we call it as a partial journal bearing. So for the derivation part, I am considering a full journal bearing where the journal and the bearing is concentric. This can only happen based upon the following assumptions, but generally this will not occur. So as an assumption, I am considering the first one as the load acting on the journal is very small, such that the journal and the bearing is concentric, and the clearance is completely filled with an oil such that the effect of end leakage is neglected. End leakage means at the z direction, this is y direction, this is x direction. Along the z direction there is no end leakage, and the oil used has high viscosity such that there is no metal to metal contact. Here the oil is completely filled and this has a high viscosity such that there is no metal to metal contact, and the journal, to be concentric, it has to run at high speed with respect to the bearing. Here the journal is rotating and the bearing is a stationary member. To determine the coefficient of friction, I am considering this journal to be in an unwrapped condition. Unwrapped means I am cutting along the length like this, such that once I unwrap it, there are two surfaces. One surface is the journal, the other surface is the bearing. So when you look at this sketch, the bearing, which is a stationary member, is at the lower part, and the journal, which is a moving member or a rotating member, is at a above member, is the moving surface, and between these two surfaces it is filled with the lubricant, and the load acting is W. Instead of saying it as rotating, I am moving it such that there is shear stress induced in the surfaces. When one surface is stationary, the other surface is moving at a particular velocity, shear stress is induced, and we define it as shear stress is defined as frictional force by frictional area. Look at this. In order to understand this C dash, I am considering this one as I'm considering the cross section of the journal. If we consider only the partial portion means here we assume that it is a journal bearing is a concentric. One side of the clearance is C dash, the other side of the clearance is also C dash. So 2 times of C dash will be the total clearance called as C. So here we consider only one side of the portion, so it is just C dash. So we understood that shear stress is equal to frictional force by frictional area. So F is equal to frictional force is equal to shear stress into frictional area. According to Newton's law of viscosity, we say that shear stress is directly proportional to rate of shear or shear strain. So tau is directly proportional to R. Tau is equal to mu into R. Mu is called as viscosity constant, and tau is equal to mu into R is shear strain. So it is velocity by the clearance. So this C dash can also be called as H, film thickness. So it is U by H. And once you look at this profile of this shear stresses, the oil or the fluid which is adhering to the moving plate will also move at a particular velocity, and the film, that oil film which is adhering to the stationary plate, will be at rest, right? So we can get this type of stress distribution. So F is equal to mu into U by H. This mu, particularly equation 2, is substituted into equation 1. So F is equal to mu times of U by H into A. U is called as the velocity, it is pi dn by 60, and A is the circumferential area, it is pi dl, pi into d into l. After multiplying, we get pi square d square n by 60, that means rpm by 60, we call it as rps. N dash is in terms of speed, in terms of rps, mu into l into c dash. So this h is called as c dash. This c dash, in order to convert into the diametrical clearance, so this one is called as clearance ratio. Psi is called as the clearance ratio. We call it as C dash by R or C by D. That means radial clearance by radius or diametrical clearance by diameter. So replacing with the diametrical clearance, that means full clearance, C dash plus C dash is equal to C, 2C dash is equal to C, C dash is equal to C by 2. So C dash I can replace it as C by 2. So we can get an expression called as frictional force is equal to 2 pi square d n dash mu l by. So in order to determine the torque, we say that it is a product of force into perpendicular distance. Here the force is nothing but the frictional force into radius. Radius is d by 2. On multiplying, we get it as mt is equal to frictional force is this into d by 2. We get it as pi square d square n dash mu l divided by psi. Next we require COF. COF is the ratio of frictional force by applied load. This frictional force and the applied load will be mutually perpendicular. So applied load is in the y direction, and in the x direction we get it as the frictional force. So these two will be mutually perpendicular. So we say that frictional force by applied load. Here the applied load is W. So W, we need here a projected load or the unit load. Unit load is nothing but the load divided by the projected area. If suppose to determine the projected area, if I pass a light on it, we get a rectangular surface below it. Rectangular surface, we get a rectangular projected area, which is nothing but the dimension will be d into L. That is called as the projected area. So d into L. So load divided by dl. So I am replacing this term W by P into dl. So P into dl. On simplifying, we get it as 2 pi square into mu n dash divided by P into 1 by psi. This expression is called as the Petrof's equation for determining the COF. There is one more equation called as Mackey's equation, which is being given as Ka into mu times of n dash divided by P into 1 by psi the power of 10 raised to the power of minus 10 plus delta mu. So this you can find it from our equation from the handbook Lingaya volume 2, equation number 24.22, where Ka is a constant for a full journal bearing and for a partial journal bearing it is 5.4, and these values are given in the handbook. Beta is the attitude angle. So this beta refers to full journal bearing or partial journal bearing. If it is a full journal bearing, we say that beta is equal to 360 degree, and if it is a partial, whatever the angle which they have given, either it may be 120 or 60. Delta mu is equal to 0.002 for end leakage factor. A is the bearing pressure. And there is one more method to determine the COF. It is by Raimondi on Boyd's curve. So this can be determined from the handbook by referring the figures. So first we determine the Sommerfeld number. Sommerfeld number S is equal to mu n dash divided by P into 1 by psi square. This Sommerfeld number is very important to determine whether the bearing is a lightly loaded bearing or a heavily loaded bearing. So it will differentiate between those. And B is nothing but the length of the bearing in the direction of motion. So suppose B is nothing but in the direction of motion. So this dimension we call it as B. If we take it as a rectangular plate like this, B is nothing but in the direction of motion, in the direction of U, whatever the dimension is there, that is B, and perpendicular to the direction will be L. So this is an expression. Also, to determine the power loss, there is one more equation called as frictional force into the velocity. Frictional force already we have determined. Velocity pi d n dash, that means it is in terms of seconds, rps. So n is equal to 2 pi q d square n dash and n dash square mu l divided by psi. So these three equations are sufficient to determine the problems, whatever the problems which is related to coefficient of friction and power loss and torque, we can solve to understand better.